Yeah.
Okay, it works again. Okay, yeah. And first of all, I was working on the well-postedness of the inner dynamics of a Port-Hamiltonian system, and then I was working on stability or stabilization of the wave equation in this framework, and finally I will present some compactness results. Okay, so the system or the inner dynamic of the system is given by the following PDE, and X is the state variable, P0 is just a exclusive matrix, and H is a strictly positive, or is for each entry it's strictly positive, and invertible is the Hamiltonian density. Okay, there are no inputs and outputs so far. This is because, first of all, I need to handle the inner dynamics. The inner dynamics need to admit solutions and uniqueness, and then I will add an input and an output, the so-called ports of my system. Okay, this formulation already fits the 1D case if we just set n to 1. And the question, which I already told, is which boundary condition make this system well-posed? So, I mean, existence and uniqueness of solution. And for doing that, I will introduce some notations. And for a family of Li's, of matrices, and the normal vector, I will define L partial, which is just the differential operator which appears in the upper right block of the differential equation, and L nu is a boundary operator where we just replace the differential entries with the entries of the normal vector. Okay, there is the same thing for the transposed family. And we have the maximal domain for this differential operator. So we have to understand, first of all, we have to understand it in a distributional sense, and then we can say what it means that the derivative is in L2. Okay, and with this new notation, we can write it in a more compact way, and we also use the following convention that we regard the state as all the states simultaneously distributed on omega. So instead of writing xt theta, we write just xt, and yeah, then we can write the PDE in an ODE, an abstract ODE, with the following differential operator and some. Okay, we don't really have to care about this term because it's a bounded perturbation of this operator, so it's not really important for well-postedness. Okay, we define this differential operator as A, and we give another inner product on our state space L2, which is the energy inner product, or give us the energy norm. And we have a further constraint, and we want our solutions to be non-growing in the energy, which is somehow physical meaningful. Okay, so the change of energy along a solution is given by the following equation. We can derive the energy, and then we only have to apply a product rule for inner products, and then we apply the differential equation, and then we just have the real part of AHX with X in this energy inner product, and we can okay, we want this to be negative, such that our energy is non-growing, and we can this means dissipative, and we can reformulate this in the L2 inner product just by writing an extra H and this 2 factor. And now if we substitute HX with just an Y, we can see that this is equivalent, that only A is dissipative. So we can also drop the H in our free theory, so it doesn't matter if we have an H or not. So the original question can be reduced to which boundary condition make only A generator of a contraction semigroup. So far, so good. And now I want to give an example. So there are also, it's not only from a mathematical view interesting to play with this class of differential equation, there are also relevant physical examples. And if we take, for example, the rotational operator, we can write rotational operator as a matrix vector product. And we can expand this, this matrix, and then we can see we have an L1, an L2, and L3. And altogether, the corresponding L partial is just the rotational operator. And for the boundary operator L new, we can just replace the partial derivatives by entries of the normal vector, and then we get that the somehow natural boundary operator to the rotational operator is the cross product with the normal vector. This is not really surprising, but it's nice that it fits in such an abstract way. Okay, and since the LIs are skew-symmetric, we can easily calculate the L partial transposed, which is just minus the rotational operator. So all in all, if we write down the dynamics of the corresponding system, it's just a very simplified version of the Maxwell equation. So if we insert an Hamiltonian density and some P0, then we can make it more adequate. Okay, so back to the solution theory, we need one important tool for all of this are boundary triples. And the boundary triple is just a Hilbert space with two boundary operators. Normally, the Hilbert space is a boundary space, such that this boundary operators maps from the domain of our differential operator into the boundary space, and they satisfy an abstract green identity, and the combined mapping is surjective. So we aim to find such an abstract green identity for our differential operator, and to get this, we'll see that there is a integration by parts formula for our differential operator. Okay, we skip this. It's not really surprising. If we take the sum of these two inner products, we get the inner product on the boundary, and there this L nu comes, and this is also the motivation for introducing L nu. So for our actual differential operator, we have these two inner products, and we can write it as 4 inner products by reading it clockwise, and then we can apply our integration by parts formula for these two pairs. And so we can see that we almost have something like an abstract green identity. Okay, now we add a projection here on the range of this operator. This is only to make sure that both maps into the same space, but this doesn't change the value of the inner product. And now we just define these operators that appear here as our boundary operators. So we can say we are almost done, but there is one small problem. So we can summarize. We have this abstract green identity with these two boundary operators, but unfortunately, these two boundaries operator cannot be continuously extended on the domain of A, or at least not in general. So there is one way to fix it, and we can just change the codomain. We can say we don't want to, or we allow a little bit more than L2 on the boundary. And this is where Quasi Gelfand triple come into play. Just to recall, a normal Gelfand triple is a triple of 3 Hilbert spaces where the two Hilbert spaces x plus and x minus are dual to each other, and they are dual to each other with respect to the inner product of the pivot space x0, and we have a chain inclusion. We can write this duality with respect to the inner product as a limit of inner products in x0. And we ask for the same in the Quasi Gelfand triple case, except that we drop the chain inclusion, and instead we have not continuous embeddings, but closed embeddings. Okay, there is a lot to say about Quasi Gelfand triple, but we won't go into details. We just say what is our situation. We have the domain of A, and inside the domain of A, there is always H1, and we can define our mappings on H1. So now we want to extend the boundary mappings, and when we do that, the space gets bigger, and the situation is the following: one mapping gets the space VL, and the other mapping gets its dual space, and altogether this situation establishes a Quasi Gelfand triple. So now we can extend our mappings, and we can rewrite the abstract green identity within these new spaces. So we can extend this for XY and in H1 to XY in the domain of A, and we have to pay the price. We have here the duality instead of an inner product, but we can also fix this by using the duality mapping between the spaces, between the dual spaces. So This is already enough to characterize dissipative boundary conditions, but there is one fly in the ointment, and this is we have to formulate the boundary condition in this strange spaces, or at least artificially constructed spaces. And to come back to the pivot space L2 on the boundary, we have the following theorem, and the following theorem says, if we have a boundary triple that comes more or less for a Quasi Gelfand triple, then we can formulate our boundary conditions within the space, within our pivot space. Okay, and in our concrete situation, our pivot space is L2 on the boundary, and our Quasi Gelfand triple are the VL and VL prime. Okay, these three conditions has to be fulfilled, but it's there are a lot of examples where you can very easily verify that these three conditions are satisfied. So the last condition may seem familiar for those of you who know the one-dimensional framework. This is exactly the condition that also appears in the one-dimensional framework. Okay, so let's put some inputs and outputs to our system. We have an input U, the inner dynamic, and a very simplified version of everything, and an output. And now we want to stabilize the system. Okay, we give a proportional feedback. K can be spatial dependent, so it can be, we can have a dependence on the boundary values. And altogether, this gives us the following boundary conditions. If we translate our feedback to their definition, we have the following domain of our boundary operator A, and that is this boundary condition. And due to the last theorem, this is a well-posed system. And when we want to see whether this is stabilizing or not, we do, as Mario said before, we do spectral analysis. So, okay, first of all, we want to make it even easier, and we take a very concrete example, and that is the wave equation. So I have to reformulate the wave equation in a Port-Hamiltonian way. So the classical formulation would be like this. We have here's the 2 is missing here, and it's here. It's okay, there's some mistake. Whatever. With the classical wave equation with physical parameters, and we fixed the wave on one part of the boundary. So, okay, this was maybe not very clever to have gamma for both the boundary operators and part of the boundary, but now there is no gamma for the boundary operator anymore. So every time I talk about gamma, it's part of the boundary. So we have part of the boundary gamma 1 and gamma 0, and gamma 1 is the other part of the boundary. And by choosing this state variable, we can reformulate the wave equation in the following form. And now there's one important thing which somehow is a new aspect in multidimensional Port-Hamiltonian systems, and this is we have to take care what in which spaces our state variables live. We cannot, or we can do it, but it sometimes leads to strange solutions. Take just L2 times L2 for both entries. Okay, we have the following equation. We will drop the Hamiltonian because it's not really necessary. You can easily get the same result for an Hamiltonian. It's not really necessary, not really important for the theory. Okay, so we have this inner dynamic with this state variable, and now we can see the second component is a gradient field, always. So before, when we just care about uniqueness of solution, we can choose the state space L2 and L2, but it doesn't fully respect the structure, because the second component is a gradient field, and therefore it's more meaningful to also reflect this in the state space. And so a better state space would be L2 and gradient fields. And when we look at this, it's even if we want to make sure our boundary condition is fulfilled, we have here 0 on one part of the boundary. So the domain of the domain of the differential operator is then just the same, and we intersect the domain of the maximal domain of the divergent operator with this new part, or with this restriction. Okay. So now we can we go back to the situation where we were, and we use the situation. We use the wave equation. So this changes to the normal trace and to the Dirichlet trace. And we have this boundary condition just on the other part of the boundary of gamma 1. And here we already respect the boundary conditions that it's fixed on one side. Okay, and now to check whether this is a stable system or the feedback is stabilizing, we do spectral analysis. So we calculate the Resolvent set, and we assume that we have a non-zero lambda, and then we have to check whether we can solve this equation. So we split our variables into with respect to this block form, and then we have these two equations. We can multiply the first equation by lambda, and the second equation we isolate lambda x2, and then we substitute lambda x2 by what the second equation gives us. And then we end up with some kind of Helmholtz equation, and we also still want to respect the boundary conditions. So we have the second line, and here also appears, okay, I multiplied the boundary conditions also with lambda, and now I can substitute also in the boundary condition, I can substitute lambda x2, and then I end up with this form. Okay, we can, with some technical tricks, we can also remove L2 from this equation, F2 from this equation, such that it's really, here we really have the Laplacian, and here we have Robert boundary condition. So this is a Helmholtz equation with Robert boundary conditions. So we can use Helmholtz theory to say for which lambda this is solvable. And it turns out that it's solvable for all lambda on the left complex plane. Except for 0, of course, because if lambda is 0, then there is no coupling. So these are isolated equations. Okay, and there is one more thing. It's nicer to have a compact resolvent, because then we have only eigenvectors and no strange spectrum. And this is why we want to show that, or maybe one thing first, and this is why it's important to have this different or this adequate state space, because if we wouldn't have this adequate state space, if we just look at the normal L2 times L2, then we can construct with a phi in non-zero phi. Okay, maybe I need compact support, but this is not really important. We can define a constant solution for our problem. And this is, we just choose x1 to be 0 and x2 to be this somehow two-dimensional curl operator with zeros. And then we can easily see if we apply, okay, if we look at the left-hand side and we take the time derivative, then this is clearly 0 because this is time independent. And if we apply it on the right-hand side, then okay, the gradient of 0 is 0, and the divergence of this vector is also 0, because we can just use Schwarz's theorem to switch the order of the derivatives and then see that it's 0. So we have here a vector. This is a constant solution of our problem, which is also an unstable solution. And this cannot happen because this cannot happen if we have an adequate state space, because this is, okay, you can, with a decent amount of time, you can see that this is not a gradient field, what I've chosen here. Okay, so we can fix it if we intersect the second component with gradient fields. And there is one thing that is important to, or for stability, it's important for the stability result, and it's the compactness result. And if we look at the domain here, it's already clear that we can compactly embed this space into L2. But it's not clear if we can embed this space into L2 compactly. So we have to work here. And this is actually you can say actually a corollary of a bigger result, but it's in the corollary, it's easier to see how the proof works. If we have this domain, sorry, I'm way ahead. So first of all, we can get the following result. This is semi-uniformly stable. The semigroup that is derived by our feedback system. And this one tool to show that is the compact embedding, and I want to show this compact embedding.
What is semi-uniformly stable?
Yes, okay, semi-uniform. You told it before, I guess, but
I'm sorry.
yeah, but it is some concept between exponentially stable and asymptotically stable.
So it's f of t. The normal semigroup is the solution is less than f of t times the norm in the domain. That's semi-uniform stability.
So if I can you say it again?
You can say trajectory, let's say x of t, its norm in the state space is smaller than some function f of t, which goes to 0 times the norm of the initial state in the domain.
Yeah, right.
That's the definition. Okay.
Yeah, that's the definition, right? You can, yeah, and you can also get some results at which speed this goes to 0. If you look at the Helmholtz theory, but you need further assumption. The Helmholtz theory delivers some decay rates, but you need extra assumption for this to work.
So I put the question because I'm maybe not as old as Enrique, but I have a result from I'm old in fact from '98, which says that you have a compact embedding of DFA in X, and you have strong stability.
Yeah.
Then you have what's called semi-uniform stability.
Yeah, yeah. Okay, this is more or less what I'm using.
Yeah. So that's 98.
Okay. Yeah. So I'm. So you can say I'm recycling old results.
It is strong stability. That's an assumption. That's an assumption, and then I also assume that the embedding DFA in X is normal.
Yeah. So
I send you this. It's a proceedings. Nobody knows about it. So I will send you.
Okay, so so what I want to show is how you can derive this compact embedding of the space, and I have to point something out because this is important. I think you can see it. I can't because the Zoom is in the way. But for those of you who are online can see this.
No, but you can make smaller that window.
Yeah, it's okay. Yeah, okay. So this boundary condition also tells us that the normal trace is in L2 and it's bounded because this part is bounded. So we can if we just want to look at this one isolated, we can also take this information into account. So we know that this part is in L2. So, and this is what we are doing. We look at our space X, which was more or less the same from before, the second component. And we define a norm, and then we say we can compactly embed this into L2. And the proof of this is very easy. I mean, there is a bigger result, but if we just reduce it to this case, it's very easy to understand the proof. If we take a bounded sequence in X, and without loss of generality, it's bounded by 1, then by definition, here there is another sequence phi n, such that the gradient of phi n is Fn. This is by definition. And by the Poincaré inequality, also phi n is bounded in L2. But also the gradient is bounded in L2. So phi n is bounded in H1 and also in H1 half on the boundary. So by compact embeddings that we already know, H1 and H1 half, phi n is a Cauchy sequence in L2 on omega and L2 on the boundary. Okay, and now we can use that to show that also Fn is a Cauchy sequence just by calculating the difference in the L2 norm. We can by using the square, we can use the inner product, and by definition, the gradient of phi n is Fn. So now we use an integration by parts formula to move the gradient on the other side. Then we get a divergency. We get the boundary term, and now we just use Cauchy-Schwarz. And we use the boundedness of the sequence Fn. So this is bounded by 2. And now we have, since phi n and is a Cauchy sequence in L2 on omega and a Cauchy sequence on L2 on all of the boundary, also on this part gamma 1, also Fn is a Cauchy sequence. So this was actually pretty easy. And this is the main idea I think I'm already over time. And this is the main idea also for the general result. And the general result is somehow, okay, I skipped that. The general result is somehow a compact result for the intersection of the rotational domain and of the domain of the rotational operator and the divergence operator. And there, I skip to the point where it is known. Okay, this result is already known. If we have the domain with L2 tangential as a trace, then we know that this is compactly embedded. But now we want to have we have boundary conditions split both on for the rotational operator and for the divergence operator with the normal trace. And then we have the following theorem. We have on gamma 0, we have the tangential boundary trace, and on gamma 1, we have the normal trace. And then we can, or what I did is I showed that there is a compact embedding also for this space. So somehow it will be possible to do the same thing with the Maxwell equations. Okay, and this is where I want to stop, or I should show my references. So the first part was, or is already published, is the well-postedness of linear Port-Hamiltonian systems. Then the second part was stability of the wave equation. And the third part was the compact embedding of the diff-curl system. Okay, and future plans or future direction could be higher order Port-Hamiltonian systems. For example, the Kirchhoff plate is of second order, and stabilization for general Port-Hamiltonian systems. And for that, you need this compact embedding is very important. So the Maxwell equation might be possible, and also for the midland plate, it will be possible to find a compact embedding. And then another direction would be spatial dependency of the LIs, but I don't know. I don't know any examples where this is necessary. And also the thing is that you give all spatial dependency in the Hamiltonian density, so maybe this is not really. It's only interesting from a mathematical point of view. And this, a third thing could be differential algebraic Port-Hamiltonian systems. Okay,